Namaste and welcome back to the lecture on linear algebra through geometry. Um, in the last lecture we tried to look at the idea of cross product and we looked at the properties of cross product, and towards the end of the lecture we left with a question where we said that look, if we are going to have 3 linearly independent vectors, I mean they will they and you have a parallelepiped formed with the sides being along the directions of the 3 linearly independent vectors. We left with a question as to what is the volume of this parallelepiped. Initially we saw that if you had 2 linearly independent vectors in 3 dimension space and we had a parallelogram whose sides were along these two the directions of these 2 linearly independent vectors, we figured out that the area of the parallelogram was basically the cross product of the 2 vectors, the magnitude of the cross product of the 2 vectors, that is what we had. And in fact we had area, we also looked at area of the parallelogram to be the I mean through the Pythagoras theorem also, generalized Pythagoras theorem also. Now what we do is in this lecture we try to find out the volume of the parallelepiped and go ahead with looking at the ideas of lines in 3D, planes in 3D and so on. Okay. So let us go ahead with the lecture to find out the volume of the parallelepiped. So suppose we have let U, V and W be 3 linearly independent vectors in R3. Now what do we mean? None of the vectors none of the vectors here can be expressed as a linear combination of the other 2, therefore they are all in 3 different directions and we say that these 3 are linearly independent. Now what we want is we want to look at what is the volume of the parallelepiped which is formed or which is determined by these 3 vectors. So let us look at that. So this is my E1 or this is my x1 axis, this is my x1 axis, this is my x2 axis and let this be the x3 axis. Let us mark those 3 vectors u, v and w. Let me take u to be this vector, let me have v to be this vector and let us take w to be this vector. Now what we see is let us complete the parallelepiped here. So we get this, we have this and we have this, we have this guy, then we have this vector, sorry, let us say we have this vector and we have this and we have this vector, we have this and we have this guy and So, this is basically the parallelepiped that we have. So, the question is what is the volume of this parallelepiped? Okay. So, let us we have these vectors as we have marked here u, v and w. So, if let us look at this. So, if u, v are linearly independent, we have already said that they are linearly independent. So, we say that since u, v are since u and v are linearly independent, then the distance of the vector w, the distance of the vector w to the plane determined by u and v, determined by the vectors u and v, the distance of the vector w to the plane determined by u and v equals the length of the projection, the length of the projection of w along u cross v, since u cross v is orthogonal to the plane, and we have already seen that this distance is basically given by distance is equal to, we had this, we had w dot u cross v magnitude divided by the length of u cross v. This is something which we did before in the previous lectures. We have seen that the distance of a point to a plane which is orthogonal of a point which is the distance from a point to the plane passing through the origin and orthogonal to a vector is basically defined this way, and this is what we have. Now, this is going to be the height of the parallelepiped. So, that is basically the projection of this vector. So, this is basically the length of that projection of that vector. So, what we have is we are going to look at the volume now. So, therefore, the volume of the parallelepiped is given by we already have the base area which is nothing but base area into the height the base area is nothing but this, we have this u cross v, and the height is just what we found out, which is nothing but the absolute of w dot u cross v divided by this u cross v, and we see that these two getting knocked off. Therefore, the volume is given by w dot u cross v. So, this is the volume of the parallelepiped. Therefore, we see that if u v w are linearly dependent, w are linearly dependent, then the parallelepiped is contained in the plane and therefore the volume is 0. The parallelepiped is contained in the plane and hence the volume is 0. Which implies w dot u cross v is equal to 0, and this also goes by the name which is basically the scalar triple product. This is something which we would have studied in high school, where this is also called as the box product, which essentially we will see that this is the determinant of a 3 cross 3 matrix. So, what we see is, like, given 3 linearly independent vectors, they determine a parallelepiped, and the volume of the parallelepiped is basically given by this this is the one, the dot product of w vector with the cross product of u and v, right. So, this is what it is. Okay. Now, having done all these things, we figured out the what do you call, we found the area of a parallelogram, we found the volume of the parallelepiped and all those things. What we have still what we want to look at is a very fundamental thing, where we are going to define lines in 3D, because in 2D you can see that the lines are either intersecting lines, 2 lines you will see them to be intersecting, or overlapping lines, or they would just be parallel to each other, whereas in 3D there is something more to it. We will see what that is. So, let us look at lines in 3 dimensional space. Now, before we get into this, let's recall the parametric equation of a line in 2D. There if we recall it, we have this L of t, which was given by a particular point, say P, plus a scalar multiple of the vector v. This P was a point. I hope we remember the difference between the coordinate specific coordinate specific point and the vector v, which is basically coordinate independent quantity. So, we had L of t is equal to P plus TV, where P is the point and T is the scalar and V is the vector along whose direction T is the scalar and V is the vector along whose direction the line is. Now, there is something interesting that happens here in 3D also. We find that the representation of line, the parametric equation of the line, is basically the same. So, in 3D also the representation is similar. is similar in the sense we have another, we can say L of t is equal to, take a specific point P plus say scalar multiple of a vector V, but only thing is there is a point here P is going to be a 3 component fellow. We are going to have P1, P2, P3, and V is also a vector with 3 components V1, V2, V3, right. Now let us look at this. So, for example, I want to figure out whether in 2D I want to figure out, if I want to figure out if there are 2 lines which intersect, what is it to say intersecting lines? We know that the point of intersection is basically that point which lies on both the lines. So, let us just look at that. So, in 2D let us look at let L1 of t or L of t be a line which is given by P, the vector P, the point P plus a scalar multiple of the vector V, and another line L of S which is basically given by, let us say, Q plus, let us say, S times the vector W, right. We have S times the vector W. Now what it is to say a point of intersection, the point of intersection is basically is found by taking 2 scalars say t hat and s hat such that P plus P plus t hat V is equal to Q plus S hat W. What it means is we are going to say t hat V minus S hat W is equal to Q minus P. It is interesting to note that we have all these vectors and points in 2D. So, we must have that in mind. So, I have t hat into V1 V2 minus S hat into W1 W2 is equal to Q1 minus P1 Q2 minus P2. So, these are basically 2 equations in 2 unknowns, 2 equations in 2 unknowns, namely t hat and s hat. Now, we can solve for this and then get the value of t hat and s hat and plug it in the equation and get the point of intersection. So, that is easy to do. However, in 3D it comes with a slightly it comes in a tricky manner. So, in 3D also it is the same thing, whereas in 3D the points are going to be with 3 components. So, I am going to have L of t which is nothing but same P plus TV, and L of S is equal to Q plus SW. But if we want to try it again, we want to find the point of intersection which is basically given by P plus T hat V is equal to Q plus S hat W for some scalar, that we need to find out T hat and S hat, right. We need to find out this. Now, interestingly what we see here is the point P is going to be, point P and Q are going to be 3 component fellows. So, we have P1, P2, P3 and Q is equal to Q1, Q2, Q3, this is what we have, and we have the vector V is also V1, V2, V3, 3 component guy, and the vector S is also the vector W the vector W is again a 3 component vector. Now, if you try to solve this equation which is marked as 1 here, we see that the equation is going to have so we are going to have, this implies we are going to have t hat into V1 V2 V3 minus S hat into W1 W2 W3 is equal to Q1 minus P1, Q2 minus P2 and Q3 minus P3. Now, it is interesting that we have two unknowns, namely T hat and S hat, but we have 3 equations. So, this basically becomes an overdetermined system. So, this is an overdetermined system, overdetermined system in 2 variables. Basically, what is it to say overdetermined system? I am sure this was there in the very first module. We will just recollect this. This is 3 equations in 2 unknowns. In 2 unknowns. Now, this may have a solution, may not have a solution. There are, that it may not have a solution can correspond to 2 cases here. One, we already know that the lines can themselves be parallel, so you will not have a solution. In the other case, that is exactly where the 2 lines in 3D can pose a problem, because in 3 dimension, if you look at this, let us take our E1, E2, E3 axis and let us draw this unit cube. It may so happen that the lines that we have can be one along here and one along here. That means they are in 2 different planes. These are basically called as skew lines. If the lines are skewed, then we do not get a solution. For example, there could be another line which is basically here and another line which could be here. So, these are basically lines which are in parallel planes. And these are not parallel lines. I mean, you cannot bring in the idea of parallel lines here, for the simple reason that, okay, one of them could be, as we see here, one of the line is along that edge and the other line is basically along this edge. So, there is no question of parallel and things here. So, what we do is we look at skewed lines here, which means you may not have solution. So, when we solve system of equations with 2 unknowns, we actually get into the problem of skewed lines, in which case you will have no solution. Okay. Then as far as the planes are concerned, we have already defined the we have defined planes in 3D or a plane in 3D. We defined a plane in 3D through the okay, let us take this, let P pi be the plane passing through the origin and perpendicular to a vector u. So, the equation of the plane is given by equation of the plane is given by let us say y dot u is equal to 0, where y is any vector on the plane p pi, and we actually found out the distance from a point to the plane. We also found out in the previous case, we also found the distance from a point to a line passing through the origin. We found all that. So, the next thing that we want to look at is we want to look at what is the intersection of a line and a plane. So, we want to look at the intersection of line and a plane. We are going to look at what happens when a line intersects with the plane, and what is the intersection point of a line with the plane. So, that is what we are going to look at. So, how is it? So, assume that we have the same, let us say this is our x1 axis, let us take this as x2 axis, and let us take this as x3 axis. Now, what we do is like assume that I have a plane here and I have a line which basically intersects this plane at this point, right. Let the line intersect this plane at this particular point. Now, so what are we going to do? We want to figure out what is the point of intersection, especially when a line intersects a particular plane, right. So, we are going to look at that. So, let us call this as the plane P and let us call this as the line L, and let us do this. So, given a plane P, and a line L, now we ask this question, what is the intersection point what is their point of intersection. So, what is the point of intersection? So, let us assume that let us take Q to be a point on the plane. So, let Q be a point on the plane with coordinates, let us say Q1, Q2, Q3, right. Let Q be a point on the plane Q1, Q2, Q3, and let us take N to be a vector orthogonal to the plane, orthogonal to the plane. That means, we can also call this this n vector is also called as the normal vector to the plane, right. It is also called as the normal vector to the plane. So, what do we want? We are going to look at the unknown point of intersection x. So, this is basically my, let us take this as the point x, right. Okay. So, let x be the point of intersection let x be the point of intersection of the line and the plane since it is the point of intersection. X must be on the plane And now what we are going to do is we are going to look at this. Since q is a point on the plane, q is a point on the plane, is on the plane, and x is also on the plane, we can find a vector. We can basically find a vector which is from the point x to the point q, we can find a vector which is basically given by, let us say this. So, since q is on the plane and x is also on the plane, it must satisfy x minus q dot n is equal to 0. So, basically this is a vector, x minus q is a vector that we will get. So, x minus q dot n is equal to 0. So, by definition we also see that x is also a point, is also on the line given by a point P on the line and a vector v. That means you can say the point x is equal to p plus tv, which is the parametric equation of our line which we already had. So, p plus tv we have. So, we do not know the correct value of t. So, what we will do is we need to find that value of t which will actually solve the problem, right. So, we have this as equation 1 and we have this as equation 2. Now, substituting 2 in 1, we get p plus tv minus q dot n is equal to 0. So, what we have? We have p minus q dot n plus tv dot n is equal to 0, and therefore, we find t is equal to, we get the value of t which is nothing but q minus p dot n divided by v dot n. And now once we get the value of t, once t is known, we can find the value of intersection, we can find the point of intersection, we can find the point of intersection x given by intersection x, which is given by p plus tv, which is p plus q minus p dot n divided by v dot n, and that is the point of intersection that we have. This is the point of intersection. Okay. So, what we have done in this entire module, to summarize, we have looked at the definition of a vector in 3D, as something with 3 components. Then we said that we are going to look at the projection of a vector onto another vector, projection of a vector onto another, Then we looked at the distance. In fact, even before looking at the distance, we actually defined, or we looked at the equation of a plane passing through the origin, equation of plane passing through origin, and orthogonal to a given vector, We looked at the distance from a point, to the plane passing through the origin, and orthogonal to origin and orthogonal to a given vector. We also looked at the distance from the point to a vector, distance from a point to a non-zero vector, we looked at the area of a parallelogram in 3D. That turned out to be the cross product of the two vectors. We looked at the definition of cross product, we looked at the properties of cross product. We went to figure out the we looked at the idea of linearly independent or dependent through the cross product, linearly dependent or independent. We looked at through the cross product of two vectors, of course, of two vectors in 3D. Let me rewrite that, of two vectors in 3D. Then we looked at the volume of a parallelepiped. We looked at the idea of skewed lines. We looked at the idea of intersection of a plane and a line. We did all these things, and from here where do we go? We are going to look at linear maps like what we did in 2 dimension. We are going to look at the idea of linear maps in 3 dimension, where we will again revisit the notions of reflection, shear, scaling, and projections and all those things, followed by of course eigenvalues and eigenvectors here. And later we will also look at Gauss elimination. We will look at system of equations and then try to understand the system of equations through the vector approach. And in subsequent modules we will look at the idea of linear space, vector spaces, we will define vector spaces and so on. So for now the next module that we will be looking at is linear maps, determinants and volumes, and we are going to look at eigenvalues and eigenvectors in 3 dimension. Thank you.